Okay, I want to do the same problem as I did in part one, but I'm going to change one thing. I'm going to calculate the angular momentum about a different point in this particular problem. What I'm going to do in this part of the video, I'm going to actually, when I conserve angular momentum, I'm going to calculate the angular momentum about this point, actually anywhere along this blue line that passes through the bottom end of the stick. Okay, what I'm going to be doing now works for any point along this blue dotted line that passes through the end of the stick. When I do this, though, when I write my angular momentum of the rod, it's going to be a little bit different. And I'm really using Chagall's theorem to do this. I'm going to write this in terms of the angular momentum as the angular momentum of the center about the center of mass plus the angular momentum of the center of mass. Okay, the angular momentum about the center of mass plus the angular momentum of the center of mass. Because we've chosen a point not at the center of mass of the rod, but somewhere down here. Remember, the center of mass of the rod is somewhere over here, a distance L over 2 above this point. And so, even though I choose this point, I should be able to get the same answer. I better get the same answer. And so what I'm going to do is, I'm going to go back and set up the equations. I'm going to set up the equation for conservation of linear momentum. Remember that this object's coming in with some velocity v naught. So my initial momentum is little mv naught. My final momentum of the system, consisting of the two objects, is mv final. And then the momentum of the center mass of the stick, or the rod. And I'm going to use capital M for the mass of the rod. And again, what we're going to do is rewrite this equation. This is the same as what we had before. What's going to be different now is our equation for the angular momentum. Well, the angular momentum about this point, we're going to use R cross P again, but when we do R cross P, it's going to involve the entire length of this rod. And again, the angular momentum is going to be clockwise. Likewise for the angular momentum afterwards, you're going to have an expression that looks just like that. Now, here's the thing that's different is the angular momentum of this rod is not going to consist of two parts, not one. And in part one of the video, when I calculated the angular momentum about this center mass, my angular momentum of the stick only consisted of one part, just I center mass times omega. But now we're calculating about this point, and so we need to write the angular momentum as the angular momentum about the center of mass plus the angular momentum of the center of mass. Okay, so what are we going to get from this? Well, the angular momentum of the center of mass, remember the center of mass is L over 2 above this point. And the next thing is the angular momentum of the center of mass, or about the center of mass. Okay. I also want to do the same thing I did in the previous video. I want to solve this for omega. All right, so what is omega going to look like? We're going to do a little bit of algebra. Again, I'm going to skip some steps. I'm going to get the following. Omega is going to be equal to m times L times v naught minus v final minus big M over 2 little m v center mass over I center mass. So now omega looks much more complicated here than before. In part 1, we had a much simpler expression. In part 1, we end up getting something like this. I got the following expression. So this is what I got in part 1 when I calculated the angular momentum about this point, but now I'm doing it about this point. So it looks like I'm going to get something completely different. It looks like the problem is a lot more complicated. Well, the problem I have right now is that I have this added term, and I have an expression for v center mass. So I need to take this and stick it in here. And then I can compare it to this. And if I get the same thing, then I'm really going to get the same answer as in the previous video, because this equation was the same in the first video. And then when I write the third equation, you'll see it's going to be the same as in the first video in part 1. Okay, so let me now do a little bit of algebra. I'm going to take this expression and substitute it into here. And let's see what we get. I'm going to do it in purple. And I'm going to write it over here. So I'm going to take this and put it right here. So you get this cancels with that, this cancels with this. And what you're going to get is V naught minus a half V naught and minus V final plus V final over 2. And that's going to give us and if I factor out the 1/2, I actually end up getting the same expression for omega. This is the same expression now for omega as I had in part 1. Okay. Which tells you right away that you're going to get the same answer. Well, I need to also write down the equation for the kinetic energy. So let's do that. And I'm going to write it. I'm going to write it. Let me erase this. I'll write the last equation here. Unfortunately, I don't have a lot of space. So I'm going to start with my initial kinetic energy of that object, and then my final kinetic energy of that object is going to be this. And then the rod's going to have kinetic energy of the center mass and the kinetic energy about the center mass. This equation and this equation are exactly the same in part 1. And when you do the substitution here, you get the same expression as in part 1. And so you have the same equations, you're going to get the same answers. I don't have to go through the math. So the purpose of this is to show you I can choose really any point to calculate the angular momentum, and I should get the same answer in this problem. It seemed like it was more convenient though to choose the center of mass instead of this point.